Well, hello everybody. I'm back to do another part on the tube theory. I believe this is part 3. I'm going to try to cover some ground here. I'm not sure how far I'll get along. I'm going to start out with the different classes of amplifiers. There's actually a lot more than this, but in tube amplifiers we've got basically 5 different types, and there's actually a few extras on top of that we won't really concern ourselves about. The 3 primary ones, Class A, Class B, and Class C. And basically what this means is where, when you bias the amplifier, is where you actually set the operating point. Now as we go through them, that'll be a little more self-explanatory. When you look at a graph where on this axis here, the x-axis right through here represents the plate current. The axis down here, the y-axis, represents the grid voltage. And this along here is actually what is known as a load line. Now, it's actually where you can set a different levels of bias. Okay, on a Class A amplifier, we pick a spot about halfway up between this point, which is known as the saturation point of a tube, and this point called the cutoff. Now, we pick this point, it's about halfway in between, and basically all what a Class A amplifier is whatever input signal we put in, our output signal will be a full wave. In other words, we get both the upper portion as well as the bottom portion of the wave. And that's all there is to a Class A amplifier. Some books and some teachers try to teach it that this wave has to be non-distorted, but that's not the true definition. The true definition means for Class A that you get a full output wave with whatever voltage you put in. Now this is your signal voltage, and it translates out to this output. And that's it for Class A amplifier. Now the next one is Class B. In Class B, we move our operating point from about midway and we take it to cutoff. Now at cutoff, part of the signal, input signal, is not going to get through the amplifier because it's below the cutoff point. So this negative sides here of our signal going in will never get amplified. Only the positive going gets amplified, and that's reflected in our plate current output. You only get half the wave, and that's it. And that's basically all there is to Class B operation. Now there's 2 others that deal with Class B, and it's actually a mixture of A and B. The first one is Class AB1. Now what you do with a Class AB amplifier, you move up your operating point up a little ways so it's away from cutoff, but not clear up to the midpoint. This way, with your input signal, part of your input signal will not get through, which is shown reflected by the cutoff right here. You get your full positive going, but part of your negative is cut off. Now, there's Class AB2, and the big difference between the two is in Class AB1, the input signal never goes positive. In other words, the grid will never go positive. It stays on the negative side. In Class AB2 operation, we allowed to take our input signal and move the grid positive. Which what it does is allow a much higher output in the positive going signal. It goes clear up to about basically almost saturation point. Again, the negative half will stay about the same. There's not much difference. But if you look here, our positive signal stopping off about right here. We're over here it's clean up here, pretty much near saturation point. So that's the two differences of those. I'll get into when I deal with power amplifiers, which we'll get into in a couple videos, the difference between these two, why we would want to use either AB1 or AB2. The last one is Class C. In Class C, we go way past the cutoff point and we set our operating point. That way only very little bit, and this is exaggerated, these curves, but only a small portion of our input signal ever gets through and produces an output. Now, in a lot of Class C operation, the output may not even be near as big as this, because generally the input signal is not near as big, and it's actually not as much of this is going in there. Now, where do you find these amplifiers and why the differences? Class A is the most common used, mainly because it's giving you a full wave output, which makes it a lot easier just to have an amplifier. You don't have to do anything else. You don't have to have any other special circuitry or anything like that. You can keep a tube count down. Several different things you can do with it. But being that the current is running constantly in the tube output and through the tube, these are the least efficient amplifiers. Generally somewhere between 10 to 25% efficiency, depending on the tube, depending on the amplifier, depending on the circuitry. Class B, and in a lot of cases Class AB, both of these are generally used in push-pull amplifiers. Now, there are push-pull Class A amplifiers as well, but a lot of times they'll use these as opposed to Class A primarily for efficiency. As you appear here, I'm only running my current half the wave, so half the time there's no current going through the tube, so the efficiency goes up. These will run upwards to about 60% efficient, 50 to 60%. AB just slightly a little less because I'm running current a little more. Class C is the most efficient of all the amplifiers. These can approach 90% efficiency. These you don't see too often. The only place you might see them is in some radios on their oscillators. They will use a Class C amp for the oscillator, for the local oscillator. You see a lot of these in test equipment for RF generators and stuff, and oscillators. They'll use Class C. The other place is a transmitter, and primarily because the efficiency is so high and transmitters are using such high current and high voltage on their tubes, if they used anything but Class C, they would run into issues with the tubes getting extremely hot. So in most radios, like I say, some of the oscillators and some radios may use a Class C operation. And then with Class B and AB, push-pull, although there are push-pull, that's Class A. That's about all to say about those. Now we're going to get into another deal about amplifiers. We're going to talk about voltage amplifiers, and we're going to talk about this little circuit here. This is actually a circuit for, well, basically it's actually a 6J5 voltage amplifier, and I'll go through the circuit here in a minute. But it's about load lines. Now, load lines is a way of not only determining the load, but also the operating point where you want to work at, and where you want to bias the tube at. A load line allows you to be able to figure out your output waves, figure out your distortion, if there's going to be any, and things of this nature, and determine what load, RL, right here, that you want to use, what size. Now, you can draw a load line anywhere. You basically, on a voltage amplifier, you pick whatever voltage your B plus is going to be. Whatever your power supply is putting out. Not your plate voltage, but your B voltage, your EBB. Now again, here's E, it just means voltage. So whatever your power supply puts out, that's one point on the load line. The other point will be the zero voltage current, maximum current that can go through the tube at any particular resistance, load resistance that you'd use. And that can be picked anywhere you want. The higher up you go with this current, the steeper the angle the load line will be, and basically the lower the value of RL. In this case, we're running 60K. The way you determine 60K is with Ohm's law. You take the voltage and you divide it by the current that you're going to use, and that will give you your load resistance. Now, as a rule of thumb, the lower this line is, in other words, the higher this resistance is, the lower the slope of the tube, of the load, within reason, will give you, well, less distortion, a little better amplification of the tube, a higher gain. The higher the angle, less gain, but what it tends to do is it can cause much less gain on the tube, but also more distortion in it. Now, there is a certain limit, and I think I said that wrong. The higher the angle, you have less gain. Lower the angle, greater gain. Distortion kind of gets worse higher up, a little better lower down to a certain extent. There is a limit how far you can go down, because the lower you go down, if you notice, your current goes down. If you get down too low, you just don't have nothing. There's no current going through the tube. Your load will be so large it takes up all the voltage and all the current going through it. So you gotta pick a happy medium. And basically, when you're doing a load line, there's certain things you gotta pretty much have in your design already set. You need to know what kind of power supply you're going to use, what voltage you're going to use here. So what is your B voltage, B plus voltage? The other thing you want to look for is input signal strength. Now, we're running 8 volts peak to peak in here, mainly so the curves can be seen. Generally, they're never going to be anywhere near that size. You may be talking microvolts input signal, such as like if you got a microphone or a phono pickup or something of that nature, or what's coming out of your detector circuit is usually in the microvolt range. It's very low. So, but that's something that you do need to know, is what size that is. The other thing is where you pick this current at. Of course, one thing you want to do is you want to stay within reasons of what the tube is capable of doing. You know, you don't want to pick such a high current that it's beyond the normal plate current, maximum plate current levels of the tube, and you find that in the tube manual. But the other point is with the knowledge that generally on voltage amplifiers, the rule of thumb is to keep the slope less steep. That gives you a better gain within reasonable distortion. And distortion is going to be another issue that you're going to have to deal with, how much distortion you want to allow. A standard voltage amplifier, as long as you stay below 5%, you're perfectly fine. The other nice thing about these is, again, you can represent out your wave. You can show your wave on here that's input signal, which is this right here. That's going to be what is coming from your whatever signal it is going into the grid. You can bring that down, pick the point where it hits the load line and the EC, which is your grid voltage. That'll tell you your IB max, your maximum current. The other end of it comes down here. That tells you your minimum current. This here is the 0 point. This is where you picked where your operating point is going to be. So this is 0 signal current. This gives you the total current change versus, which you can bring down to the bottom here, follow these lines down, and that'll give you your voltage change. Now, what you're looking for as far as distortion is you want one side of the signal to be as equal to the other side. So you can either take the voltage or the current and do the math. Simply subtract the signal, no signal current from its max and from its min, and if they're fairly equal or are equal, it will have, actually if they're equal, it'll be zero harmonic distortion in it. Where you pick your operating point will be anywhere along this. Now the best places to pick the operating point is anywhere along the straight line. That's what you want to do. These lines they start curving down here at the cutoff point, but then they start getting straighter and straighter. You want to pick somewhere on that load line where you get the best, straightest line you can get, yet staying negative. Under most circumstances, with the signal going in, do you never want it to go positive, your grid. So, if you was having, say, a signal that was, say, 2 volts peak to peak instead of 8 volts peak to peak, you could actually pick -2, because 2 volts peak to peak means I'm going 1 volt one way and 1 volt the other way. So if I pick -2 and I had a 2 volt peak to peak input signal, it's only going to get down to -1 to -3. You'll never go positive. The other thing is, like I said, you do not want to get down into these curves, because once you do, you start getting serious distortion. This is your third harmonic distortions and other distortions that start showing up in these little curve areas. So the load line can be drawn anywhere. The only set points for voltage amplifier is the B+. The other thing that you're going to look for is at some point it's going to hit where you're going to be looking at your maximum plate voltage for the particular tube. So wherever you set, compared to your input signal, wherever you set your operating point, you don't ever want your input signal to take it so that your voltage here, it's maximum 214 volts, which is perfectly fine for a 6J5. But some tubes that might be too much. So those are some considerations you got to make. As far as the slope, you can pick any slope you want. The only limitations is you don't want to get the slope so shallow that you actually literally just don't have nothing left for the tube. So steep that either your amplification factor is extremely weak, your gain of the tube is extremely weak, or you may have problems with distortion, or you go outside the maximum current the plate can go in. So you pick somewhere much lower than that. It's trial and error. You play around with the numbers. But you can do it on graphs. That's the nice thing. That's the reason why we draw load lines, is because then we can draw lines out, figure up some measurements, get some idea what's going on. But the things you need to know really is what your input signal strength is and what your B+ signal voltage is. And other than that, you can just design it out any way you want and draw the line any way you want until you get something that's a happy medium. Now, amplifier gain basically is just simply the voltage output to the voltage input. You know, how much voltage swing do I have here versus the voltage swing I got out here. And that voltage swing is represented here. And the voltage input's represented here. So that gives you your gain. Your second harmonic distortion is this nice little formula. You don't have to memorize these. These are in tube manuals. So your second harmonic distortion is basically all it is the maximum current, which is IB max, plus IB minimum, which is your minimum current, plate current. Divide that by 2 and subtract it from the no signal current, which is in this case 5.6 milliamps. That whole thing is divided by, again, IB max minus IB minimum. Again, those are these currents here. Times 100 so that you can get your percentage. Again, best case scenario is you should always below 5%. Really good audio amplifiers you can look at, really high fidelity, is less than 1%. So that's basically on these style load lines. These can be drawn any way. Your only set points again is your B+. Other than that, as long as you stay within the parameters of the tube, its maximum ratings, everything, keep your load line not real steep. That'll give you good amplification, good amplifier gain with minimum distortion. As you'll notice on voltage amplifiers, we're looking, here's the 60,000, 60K resistor, load resistor. They usually do use pretty high load resistors. But that's basically it on voltage amplifier load lines, and that's how you figure them. It basically boils down, they're not complicated, but they are trial and error, and you just do it on graph paper. And this graph that's here is in your tube manual. This is your plate characteristics, is all it is. It's plate volts versus plate current with the different grid voltages across it. So that's where you get that from, and you can just start making out various different load lines until you get something that you're real happy with the parameters you got set down and your design that you're wanting to make. Well, this video is getting long. It's going to take forever to upload, and I've got a couple more I want to do. The next one's going to be, we're going to talk about the different biasing methods. How do I get this voltage? And that's what we'll talk about. And then I'll go into dealing with power amplifiers and how you deal with those. So, and how to figure those. So until next time, thanks for watching, and hope you enjoy this video.